in the previous class, we have seen this theorem that when one has one boundary linear operator A, then that operator A can generate only one single uniformly continuous semigroup. Okay, so here this is the theorem which we have already seen in the last lecture. So a bounded linear operator A generates a unique uniformly continuous semigroup. Okay, so this is the statement of the theorem. Okay, so let us prove this theorem. We have not proved this theorem earlier. We have just stated. Now today we are going to prove this. So you recollect the statement of the theorem. Let Tt and St be uniformly continuous semigroup of boundary linear operators if limit t tends to 0, t of t minus identity divided by t is equal to a, and that is the same as this limit t small t tends to 0, capital S of t minus identity divided by t, and then we can conclude that t of t is equal to S of t for all t non-negative. Okay, so this is the statement of the theorem. For proving this, instead of considering the whole time horizon, we would consider first only a finite time horizon. That means only from 0 to some capital T. Okay, so we take a finite time horizon, but this we have fixed arbitrarily, and then at the end we would see that that we can get rid of this finite capital T. Okay, so at present we fix one capital on positive capital T, and then we take the unit the closed square that is 0 to capital T square. Okay, the Cartesian product of the closed interval 0 to t. Okay, now given this square, closed square, we take a point small t and s in this. Okay, and look at this map. So this map is sending this norm of capital T of t and s to norm of capital S of s. Okay, so this is the order pair, and we are getting another order pair. Since capital T and S are uniformly continuous semigroups, so in the norm they are continuous. Okay, so these norms are continuous. Okay, so these functions small t to small t comma s to this thing. Okay, so this map is a continuous map. Okay, so now what we have? We have a continuous map defined on a compact set. This compact set is 0 to capital T whole square. So a continuous map on a compact set is bounded. Okay, so what we can conclude there, that if you take product of these two coordinates, the norm of tt and norm of ss, so then that function of two variables is a bounded map on 0 to capital T whole square, and we name that upper bound to be capital C. Okay, so the product is bounded by C, say, for example. Okay, so we call this upper bound as C. Okay, so this is the main part where we really require the finite capital T. So this capital T should not be confused with with this capital T. Okay, so this capital T is a semigroup, and this capital always comes with a parenthesis of small t, but this is just one scalar, just a positive real number. Okay, next what we do is that we subtract both the sides. Since we already know that this limit this limit, left limit and right limit, these two limits are having the same things. Okay, so a is this limit of the both these things. So since both the limit exists, so if we subtract, that limit would also exist, and that would be 0. Okay, so if I subtract, I would get tt minus st. Okay, so we do that. So tt minus st divided by t, that goes to 0 as t tends to 0. Okay, so from this we can write down or rewrite this statement, limit statement, in terms of epsilon delta definition. So given epsilon positive, there exists a delta positive such that norm of th minus sh divided by h, okay, that is less than epsilon by tc, okay, for all mod is less than or equals to delta. So here only just renaming the variables. Instead of small t, I'm writing h. So since this goes to 0, so given epsilon positive, so given instead of epsilon, I am writing on the right hand side epsilon divided by capital T, which is already fixed. And by fixing capital T, we have already fixed what is capital C. So capital T and capital C is known to us. So given any epsilon by capital T by C is also a positive real number. So for that, we can find out one delta positive such that this fraction norm of th minus sh divided by h is less than epsilon by tc. Okay, for all mod h less than or equals to delta. Okay, this relation we are going to use towards the end of the proof. Okay, so now for the time being we go back to the main goal. Here we would like to prove that t of t is equal to s of t. Okay, if you need to prove that these two are equal, what do we need to do? We need to show that their difference is 0. So we take any, for every t, correct? So we take any t between 0 to capital T. So remember that we are not taking all positive real number real time, we are taking only a finite time horizon, okay, 0 to capital T in that horizon only. Okay, so we take a time small t in 0 to capital T, and for after fixing this small t, we can find out one n, which is Selling function of t by delta. Okay, which delta? This delta. Okay, t by delta, Selling function of t by delta. So this n is dependent on t. Okay, small t, correct? Small n depends on the time t. Okay, so this would also imply that t by n is less than delta. Okay, less than or equals to delta, correct? Because this is the way it is defined, that n is Selling of t by delta. So t by n is less than or equals to delta. Okay, so I should have written equal, less than or equals to here. Okay, so now what do? We look at this difference norm of tt minus st. We need to show that this is 0 indeed, actually, correct? So now for showing that, what we do is that we are going to rewrite this. Okay, we rewrite using some kind of telescopic sum. Okay, so what we do is that we rewrite capital T of t is equal to capital T of n, we multiply and divide by n, t of n t by n, and then there is nothing, so I can think this is identity operator. So S0 I write, because S0 is also identity, because S is a semigroup, and then here also identity times s of t, identity I write t of 0, and s of t is rewritten as s of n t by n. Okay, just multiply and divide by n. Okay, so this thing is rewritten this way. And now here, so this difference I would like to write down as telescopic sum of many small differences. So what we do is that we are going to vary this n minus 1, n minus 2, etc. Okay, till n, this would be like 0, and here I would also increase from 0 to up to n times t by n. So this is the main idea of this simplification. So here we write capital T of k t by n. So imagine k is equal to n. When k is equal to n, it is t of n t by n, and n t by n is t only, so this thing. And when k is equal to n, n minus n is 0, so it is like this 0. S of 0 times t by n, this is 0, so this thing. When k is equal to n, so this term is like this. Okay, and from this term we subtract the term where k is replaced by k minus 1. observe here carefully, t of k t by n, and here I have t of k minus 1 times t by n. Here I have s times n minus k times t by n. Here I have s of n minus k minus 1 times t by n. Okay, so here k is replaced by k minus 1. So that is why I call this as a telescopic sum. And then the last term here, what would survive the telescopic sum from here, where k is equal to 1 would occur, because this is from the first term where k is equal to n occurs. So this would should appear actually when k is equal to 1 occurs this term. So let us cross verify here. When k is equal to 1 happens, then t of 1 minus 1 is 0, so t is 0. And then s of n minus 1 minus 1, 1 minus 1 is 0, so s of n, so s of n. So it is clear that, okay, this difference is written as this telescopic sum of small differences. Okay, so this norm is outside. Okay, norm here also there is a norm. Okay, so okay, so now norm of sum is less than or equals to sum of norms. So use this triangular inequality to write down that this summation k is equal to 1 to n norm of capital T of. So here what we do, this part we do a little more simplification. What we do here, that t of k t by n is rewritten as t of k minus 1 times t by n times capital T of tn. Okay, why do we do this? Because we would like to take common. So this part is already present here, and here this time is a little more. So it is t k minus 1 by times t by n, here t k times t by n. Okay, so here we can use the semigroup property of capital T, and that is that t of kt by n is same as k minus 1 t by n plus composition with t capital T of only t by n. Okay, so we do that. So from here we take common of t capital T k minus 1 t by n. So what remain is without k only t by n, so that I'm writing here capital T of t by n. Okay, and from right hand side I have here Sn minus kt by n. Here I have Sn minus k and minus plus 1, correct? Sn minus k plus 1 t by n. Okay, so if I take this common, Sn minus k times t by n, okay, so then I can write down t capital T of t by n here. And from here, since I have already taken common here this term, here I would get nothing identity. However, here I have s of n minus k plus 1, but I have taken common s minus k. So plus 1 that would remain here. So this 1 t by n, so that appears here. So capital T of t by n minus capital S of t by n. Okay, so these simplified terms appear here. So now I think you will be able to understand that why I'm doing all this here, because we got some difference and the time interval is small enough, less than or equals to delta. Okay, so here say t by n is less than or equals to delta is there, and since that is the case, so instead of h, if you have t by n, so you can apply this inequality, capital T of, now we read like this, capital T of t by n minus capital S of t by n divided by t by n is less than or equals to epsilon by capital T by t times c. Okay, so now this small t by n I can take on this right hand side because that is non-negative number, a positive number here. So we do this. So here we have n number of sums. So for each and every term, okay, so n number of terms are this, I write n to n, and for each and every term I am now dominating this term, this capital T of t by n minus s t by n by because here this norm of the composition of operators is less than or equals to products of the norms, so that we are using. So this norm, all these norms, I mean there are three different operators, correct? So we would write down that as a product of norm of three different operators. Okay, and then these two things we are going to consider together and this separately. for the norm of difference of this, we are going to get epsilon by t by c, and then this t by n. Okay, so this part we are going to get from this part. However, this capital T of k minus 1 t by n, s n minus k t by n, all this together, okay, this together we can bound by capital C. Why? Because capital T and capital S, the norm and product of the norms of capital T and capital S, that is less than or equal to C, that we have argued here. The product is bounded by C. Okay, so I mean, as long as the entries are in the interval 0 to capital T, and that is true here because k is 1 to n, so that means this entry is at most t. This entry is also at most small t, but small t is less than or equal to capital T. So we can apply that inequality. So n times capital C is coming from this product of these two norm of these operators, and then this epsilon by tc times t by n is coming from this middle part. Okay, so now we have this upper bound. Here c and this cancels, this n and this n cancels. What remains is epsilon times small t divided by capital T. But small t is less than or equal to capital T, so this is less than or equal to 1, so we get only epsilon. Okay, so this is upper bounded by epsilon. Okay, so what was epsilon? Epsilon was arbitrarily chosen in the beginning. Okay, so given any arbitrary choice of epsilon, we have shown that t of t minus s of t is less than or equal to epsilon. So what does it mean? It means that capital T of t is equal to s of t, right? This difference, this norm is 0 actually. So this is less than or equal to any given arbitrary positive number, so that means this norm is 0. So what we have achieved? We have achieved that capital T of t minus s of t is equal to 0 for all small t between 0 to capital T. That we have proved. However, this capital T was chosen arbitrarily. Okay, we have fixed capital T arbitrarily. So whatever capital T we choose, we are going to see this is true, that capital T of t is equal to s of t during 0 to capital T. So it doesn't matter how long, how large your capital T is. So since this is arbitrarily fixed, so what we conclude that capital T and capital S, this semigroup T semigroup and S semigroups are identical for all finite time. Okay, so that is the end of the proof of this theorem. Okay.